Hello, my dear students. Today we are going to discuss on a very important topic. Okay, so let me start the class. Gradually, you can understand the topic. Okay, so without wasting time, go to the whiteboard. So I am writing the hybridization, and percentage of S character and percentage of P character. Okay, so I think the board is visible. So my dear students, if uh, I think the board is quite visible. So for SP hybrid orbital, percentage of S character is 50%, percentage of P character is also 50%. And for sp2 hybrid orbital, percentage of S character almost 66.66%, and sorry, uh, percentage of S character is 33.3%, and percentage of P character is 66.6%, almost. Okay, and for sp3 hybrid orbital, what is the percentage of S character? Percentage of S character is 25%, and percentage of P character is 75%. So it is a simple mathematics. So there is no critical views on this. This is a simple calculation. So in view of this table, now we are going to discuss the hybridization of H2O. Okay, so I request all of my dear students to please write down the things. Please write down the things. Don't watch this video if you don't have your notebook handy. Okay, I am suggesting you to keep your notebook handy while you are watching this video. Okay, my dear students. So now we are going to discuss the hybridization of H2O. Okay, mind it, the hybridization of H2O water. So I am removing this. So what will be the hybridization of H2O? In H2O, the central atom is oxygen. So hybridization of oxygen is equals to, as our formula, half into Ma plus Be plus minus C minus A. And we are discussing the details of this derivation of the hybridization in our previous class. I will provide the link below in the description box. You can find these classes on the description box. Okay, so with the help of this equation, we can derive the hybridization of oxygen. So number of monovalent atom, Ma is the number of monovalent atom around oxygen. This is 2 because 2 hydrogens are present, and number of valency orbital electron of the oxygen is, what is the number of oxygen? Oxygen atomic number is 8. So this is 1s2, 2s2, 2p4. So valency electron is 6, and there this is a neutral atom, neutral molecule. This is a neutral molecule, so C and A is 0. So hybridization of oxygen becomes 2 into 8, that is 4. So the number of participating orbital, number of participating orbital equals to 4. So hybridization will be sp3. Okay. So number of participating orbital is 4. Therefore, number of sigma bond plus number of lone pair of electrons equals to 4. Therefore, so there are two, basically if we write the structure, the two hydrogens are monovalent, so they are attached with the oxygen with the help of a minimum sigma bond. So this is a sigma type bond, this is also a sigma type bond. So number of sigma bond equals to 2 plus number of lone pair equals to 4. So number of lone pair LP equals to 4 minus 2 equals to 2. So we can deduce the number of lone pair of H2O, which are basically, which are actually in control of oxygen. So these two lone pairs of electrons, that means the 4 electrons are the property of oxygen. So this is the structure. So what will be the structure? So sp3, that means it should be tetrahedral. But so these two orbitals, all these two orbitals are sp3. This is a sp3 orbitals and this is a sp3 orbitals, and these two sp3 orbitals, occupy a set of lone pair electrons in each. I repeat, these two sp3 orbitals, these are the sp3 orbitals because the hybridization oxygen is sp3, and these sp3 orbitals housed a lone pair of electron in each. Okay. So therefore, a repulsion, lone pair repulsion. So lone pair repulsion. This is the bond pair repulsion, and due to this repulsion, actually the shape of water is V shape. Final shape of water is V shape. Okay. Now the conflict at that till at this point till at this point the total scenario is quite okay, but now the conflict starts. The discrepancy starts now. What is the discrepancy? The discrepancy is that we think that we think that so this orbital, this is also sp3, this is also sp3, it is also sp3, it is also sp3. But the scenario is quite different. We expect that in every sp3 orbital, we expect that in every sp3 hybrid orbitals, the percentage of s character, the percentage of s character should be 25% in sp3, but it is not true here, not true in all cases. This concept is not true in all cases, what I am saying, because here these two sp3 orbitals house the lone pair. So here the percentage of s character, in that case percentage of s character is higher than 25%, and in that case percentage of s character is lower. 25%. So first point, the the equivalent hybrid orbitals sometimes behave as non-equivalent hybrid orbitals. So in case of what I am doing, I am summarizing the all things. So in case of H2O, the percentage of S character of the two sp3 orbitals occupying the lone pair uh, is greater than 25%, and the percentage of S character of the rest two sp3 orbitals projected towards hydrogen atoms is lower than 25%. So these two sp3 orbitals of oxygen, which are projected towards hydrogen atoms have S character lower than 25%, and these two orbitals of sp3 type housing the lone pair of electron with the percentage of S character higher than 25%. So all these things comes under one rule. This is called Bend's rule of hybridization. So this is called Bend's rule. So what is the Bend's rule? Now we are going to discuss the Bend's rule of hybridization. Okay, my dear students. So in our next class, we will discuss about the Bend's rule of hybridization. And my request to all of my dear students, if you have any queries, any doubts, any kinds of problem, you can write down in the comment section. If you can write down in the comment section, I'll get your problems and I'll back to you with the solution of your problems. Okay, my dear students. And one thing, please subscribe my channel and learn chemistry with utmost ease. Till then, goodbye.